Hi, welcome back to Sound School. This is part 3, the Intro to Signal Processing. So now that we've learned what a sound is and how it becomes a signal that gets into our equipment, it's time to start manipulating it. And this phase of our work is called signal processing. As we already know, signal is the electronic version of acoustic sound pressure that has been converted to electrical energy and is now traveling as electron flow through our audio equipment. Now it's ready for us to adjust as needed to make our mix exactly the way we want. Before we go too far into this, I want to be clear that there are no rules for how we use signal processing. You can and should use this stuff however you like, either in creative and adventurous ways, or subtly and carefully to preserve the original sounds. Whatever you see fit that will get your desired outcome. Try things and see what happens. Don't assume something will sound a certain way on your project just because it worked like that on someone else's. Try it, listen, and then decide for yourself if the result is what you want. Sometimes using something in an unusual way can have great results, so feel free to do things that might not make sense. There are no rules, only laws of physics. And those laws will dictate how the equipment functions on the signal, but there's no telling what the result will be on your specific sound until you give it a try. So the very best thing you can do is know and understand the laws of physics and the functions of your equipment, and then go ahead and make your own rules for how you use them. In your work, you'll encounter signal processing in 2 different forms: analog and digital. Analog processors are the real-life equipment units, also called hardware, made up of electronic components like resistors, capacitors, diodes, transistors, among other things. And these components manipulate the electronic current. They use various methods of restricting, redirecting, or amplifying that current in order to change the sound. When you grab a knob on the mixer and turn it, you're affecting the flow of electrons inside. Now, digital processing manipulates the sound signal once it gets inside a computer as digital information. To use this kind of processing, the electronic version of the signal is passed through a converter and translated into digital information, ones and zeros, or digital code. And then the computer manipulates that digital code to alter the signal. This is what's happening with your audio software inside of your plugins. When you click your mouse to turn a knob on the screen, it's adjusting the digital code. The best kind of signal processor to talk about first is equalizers, or EQ for short. We encounter EQ all over the place in our day-to-day lives, probably without even thinking about it. Every time you get in a car, you probably turn on the stereo. And you might immediately look for the tone control, probably to turn the bass up. That's EQ. On your stereo at home, there's probably a place to turn up the highs and the lows. That's EQ. With your earbuds or your headphones, you probably have an app in your phone with an equalizer on it that's processing the audio to get it the way you want it to sound. There are lots of different reasons to use EQ. We use it to improve the overall sound quality of something, or to remove unwanted noises or tones, or to enhance desired noises or tones, and finally to help blend multiple sounds together. So let's get into what's going on when you adjust these controls. Now, as we already know from previous lessons, amplitude is the height of the waveform, which determines the perceived loudness of the sound and is measured in decibels. And then frequency is the rate at which a sound wave repeats, which determines the pitch and is measured in cycles per second, called hertz. So to really understand this, we're going to use a graph that shows both of these units at the same time. This is called a frequency response graph. Up until now, we've looked at waveforms on a graph that shows them flowing over time. But now we're going to look at a capture of sound waves at a moment in time. On the vertical axis, we still have amplitude in decibels, but this time the horizontal axis shows frequency in hertz. To the left is the lower frequencies, moving to higher frequencies as we look to the right. Frequency response charts show the spectrum of human hearing. Human hearing runs from 20 hertz at the lowest, 20 cycles per second, up to 20 kilohertz at the highest, 20,000 cycles per second. Most humans can't really hear all the way up to 20 kilohertz. Maybe a baby can when it's first born, but by the time you're an adult, it's highly unlikely that you're hearing anything beyond 15 or 16K at the most. Now, 20K is still valuable because even if we can't fully hear it, it can add clarity to the rest of the signal. This is a concept that we'll dig into in future lessons. For now, you just have to understand that the frequency response chart shows 20 Hz to 20 kilohertz because it makes a nice even graph with 1K right in the center. This makes it easy to read in order to understand what the sound we're looking at on the graph might sound like in real life. For example, if we look at this, we can guess that it's boomy, humming, or thumping. And if we look at this, it's probably shrill or piercing. We can look at the frequencies on the x-axis and think to ourselves what the ranges that are represented must sound like when heard.